Hey guys, this is part 2 of the series on energy-based AI models or EBMs. In this video, I'm going to show you the unifying power of EBMs. Simply speaking, the majority, if not all, of classical machine learning as well as deep learning models can be expressed in the form of EBMs. Or in other words, the following equation will explain them all. The difference would be in how we define their energy function U. Today, I will show you how linear regression can be expressed as EBMs, and I will use the California housing dataset to clear the concepts. So this code simply downloads the dataset and stores it in a data frame. In a regression task, we know the values of most of the columns of the dataset except usually one, and the convention is to show the known columns as capital X and the column that we want to predict as a small y. This is what the following code is doing. All columns except the house price are stored in capital X, and the house price is stored in variable y. Now is the time to define the form of the energy function. Basically, I have the freedom of defining energy in whatever form I like, and every form of energy defines a machine learning model which might be useful for a task. But for linear regression, the energy has to have the following form. So we define the energy function as the square of the absolute value of the difference between the variable y and each of the other columns of the dataset, each multiplied by a free parameter plus a constant theta 0. So here x1 is the first column of the dataset and x2 is the second column. To train the EBM model and find the optimal values of the theta parameters, I need to minimize a loss function. Now, from part 1 of this series, remember that the observed rows of the dataset are most likely at the minima of the energy function. That means we want to set the theta parameters such that the energy of the observed rows is minimal. So we simply define the loss function as the average of the energies of the rows of the dataset. Now, surprisingly, if I insert the explicit form of energy into the loss function, I get the well-known mean squared error loss function of linear regression. To minimize the loss function numerically, I use the gradient descent method. So in this code, I implement the explicit form of the energy function and its derivatives with respect to the theta parameters. Then I set my best guess for the free parameters, which is most likely wrong. Then I use SciPy library to perform the minimization using the BFGS method. And here I print out the results. So here you see the optimal values of the theta parameters. Now that we have the optimal values of theta, let's insert them into the function and plot the energy function for all rows of the dataset. So most of the rows happen to be in the bin that has the lowest energy. That means, as I explained above, the most probable configuration is the lowest energy possible. But higher energies also have non-zero but lower probability. That is why some of the rows of the dataset happen to fall into those energy bins. For very high energies, the bins are empty because it is very unlikely, although not exactly zero, for rows to have those energies. And finally, here is how we make predictions using EBMs. Let's get back to the form of the energy function for linear regression. Due to the absolute value raised to the power of 2, the lowest energy possible in this equation is 0 and happens when y has the following form. And this is just the famous equation for linear regression. Therefore, if we have the values of capital X and optimal values of theta and insert them into the right-hand side, it will give us a number which would be our prediction for y. And this code uses this equation to predict the house prices shown on the y-axis, and the x-axis is the true values of the house prices. So except for the vertical line at the far right, which is perhaps because I did not remove the outliers, the overall agreement between the two and predicted house prices is acceptable. Also, I should mention that since it was not the subject of this video, and to keep things simple, I did not split the rows of the dataset into a train and test set. In a practical application, this is a crucial step to keep in mind. And this was it for part 2 of the EBM video series. Now one question for you. What would be the form of the energy function if I want to express fully connected neural networks as EBMs? Write your answers in the comments below. And if you want to support me in creating more of these courses, the most effective way would be to introduce the courses to colleagues or friends who might find them useful. And one last thing, if you need my help to go through these materials and adjust them for your own projects or your company, I run a mentorship program where I personally guide people through physics-based AI models. In this program, you get a personalized roadmap built around your goals, and you get direct access to me for questions and suggestions along the way. If interested, book a 15-minute alignment call to discuss your current level and your goal. The link is in the description.